This video will cover Chapter 7 out of the Gabrosek Stephenson textbook. Chapter 7 is all about matched pairs data. And now the term pair data means that the data have been observed in natural pairs. A few types of examples. Each observational unit is measured at two different points in time. An example that we will use here is the freshman 15. Now you've probably all heard of the freshman 15 before. In case you're not familiar, they say that you gain 15 pounds your freshman year. Well, how we could check this is we could record all freshman incoming weights at the beginning of the year, wait until the end of the year, bring them all back, and record their ending weights. Now, for this case, we do not care what their beginning measurement is. We do not care what the ending measurement is, but rather we care what the difference is between those two. And if that difference is 15 pounds, you are helping to perpetuate the stereotype of the freshman 15. Another example of this would be if I measured everybody's 100-yard dash time in the shoes that you are currently wearing, gave everybody the latest and greatest Nike Air Shock Maxes, re-recorded your 100-yard dash time. I don't care what your first time was. I don't care what your last time was. I care if there was a difference between the two. The second type of paired data, each observational unit has two different measurements taken simultaneously, and those quotation marks are there intentionally. Does not have to be at the exact same time, but nothing has to happen between the two measurements, like with the freshman 15 or the 100-yard dash example up above. Here we're just taking two different measurements. We can talk about a human being's square in terms of measurements, and that's if their height is the same as their wingspan. So we could measure your height, we could measure your wingspan. I don't care what your height is, I don't care what your wingspan is, I care if there's a difference between those. And if that difference is 0, then you are considered square. The third and final type of pair data that we will talk about, observational units are placed into logical pairs and differences are recorded within pairs. Prior to working at Grand Valley, I worked at Pfizer in the Animal Health Division. One of the things that I was responsible for was a drug given to pigs, and we wanted to make sure that the pigs still gained weight if they were given the drug. So what we did was, something else that's true about pigs, bigger piglets grow up to be bigger pigs. So what we would do is we would take the largest two piglets, we would randomly assign one the drug and do a surgical procedure to the next one, take the third and fourth largest piglets, randomly assign one the drug, do a surgical procedure to the other, on down. So we did not care how much pig 1 or pig 2 gained. We cared if there was a difference between those two measurements. We didn't care how much pig 3 or pig 4 gained. We cared if there was a difference between those two measurements. So in all three of these types of paired data, we have two measurements, and we are talking about the difference between those two measurements. And those differences are section 7.2, are paired differences. And now this will be the worst definition that I give you all semester long, but paired differences are the differences recorded within the pairs. This is the difference between the two weights. It's the difference between your height and your wingspan. It's the difference between pig 1 and pig 2. So we're going to jump all the way down to statistical inference. There is another sampling distribution here that exists and that allows us to do our statistical inference, but we will not talk about what that looks like. So we are going to do a confidence interval for the population mean paired difference. As with any statistical inference, there are certain requirements, certain conditions that need to be met in order to say that we have a valid confidence interval. The first one, of course, always being randomization, or at least a sample that avoids bias. The second, because we're dealing with means, our magic number is 30. If the data is normal, any sample size will suffice. Otherwise, we need a sample size of at least 30. And now here you might think, well, aren't there like two different groups that we're talking about? And do we need 30 from each? Well, no. There's not two different groups. There's only one group of interest. It's all freshmen. It's all students that have their height and wingspan measured, and it's all pairs of pigs. In all three of these cases, there is just one group that we are concerned with. Yes, there's two measurements, but in order to be part of the data, we need a beginning weight and an ending weight. We need your height and your wingspan. We need pig A's weight and pig B's weight. So there is only one group. Now, because we're dealing with means, we do need a quantitative variable, and because we're talking about paired differences, we do need paired data. So our confidence interval is our sample estimate plus or minus our multiplier times our standard error. Our sample estimate we are going to call D bar. This is the sample mean of paired differences. So for the freshman 15 example, we have all of the freshman weight differences. We find the mean of all those differences, and that's going to be D bar. Our multiplier is a T-star multiplier because we're dealing with means. Our standard error is S sub D over the square root of n, where S sub D is the sample standard deviation of the differences. And so our basic formula for a confidence interval for the population mean paired difference, our confidence interval equals D bar plus or minus our T-star multiplier times S sub D over the square root of n. Now this looks very, 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 very similar to something that we've done already in this class. Take you all the way back to chapter 3 where we did a confidence interval on one population mean, where we had x bar plus or minus our T-star multiplier times S over the square root of n. This is essentially the same thing. The only change between what we did in chapter 3 and what we're doing here is the type of data we're dealing with. Back in chapter 3, we just had quantitative data. And that quantitative data, we found a confidence interval for it. Here in chapter 6, we have two pieces of quantitative data. We're finding the difference between those, but once we have those differences, this just turns into a one population mean problem. In fact, that's the note that I have attached here. This is just a special case of a one population mean problem. Once we have our differences, this becomes review from chapter 3. So the rest of this, because it's review, we'll go through it rather quickly. The 35 students in a liberal arts course in statistical literacy were given a survey that included questions on how many hours per week they watched television and how many hours a week they used a computer. The sample mean difference, computer use minus TV use, was 3.36 hours. The standard deviation of the differences was 15.24 hours. Calculating 90% confidence interval for the average difference in hours spent using a computer versus watching television for the entire population of students represented by the sample. So here, D bar, our sample mean of the differences, of the paired differences, is 3.36. Our sample standard deviation of the differences is 15.24. Our standard error equals 15.24 divided by the square root of n, which is 35. That gives us 2.576. We look up our T-star multiplier for a 90% confidence interval with 34 degrees of freedom, and we get 1.961. Our whole confidence interval will equal 3.36 plus or minus 1.961 times 2.576. We plug that through, and our confidence interval goes from negative 1.00 to 7.72. And this is a confidence interval on mu sub d. Our parameter of interest here is mu sub d, the population mean of paired differences. So I don't ask for an interpretation of this confidence interval, but I'll give it to you here anyway. I am 90% confident that mu sub d is between negative 1.00 and 7.72. Or I could say I am 95% confident that the difference between computer use and TV use among all college students is between negative 1.00 hours and 7.72 hours. So is there a statistical difference between computer use and TV use among all college students? We can look inside our confidence interval. Because our confidence interval does contain 0, we go from a negative number to a positive number. It does contain 0. Therefore, there is not a significant difference because 0 is in our confidence interval. Moving on to hypothesis testing for the population mean paired difference. Our assumptions and conditions are the exact same as what they were for a confidence interval. We do need a random sample. If the data is not normal, we need a sample size of at least 30. We do need a quantitative variable, and we do need paired data. Our hypotheses, our null hypothesis is always of the form our parameter of interest, which is mu sub d, equals some null value. Now, for purposes of this class, and most of the time outside of this class, we will use a null value of 0. Now, if you were trying to disprove the freshman 15, you would probably put 15 there, but we will not do that type of example here in our class. Our alternative hypothesis will be one of these three, depending on the question being asked. Either mu sub d is not equal to 0, mu sub d is less than 0, mu sub d is greater than 0, and the usual caveat, if your alternative hypothesis is mu sub d is less than 0, you may use mu sub d is greater than or equal to 0 for your null hypothesis. If your alternative hypothesis is mu sub d is greater than 0, you may use mu sub d is less than or equal to 0 for your null hypothesis. Step 3, calculate your test statistic. We are calculating a t-statistic. This whole thing is called a paired t-test. How we calculate a test statistic is sample estimate minus our null value divided by our null standard error. Our sample estimate is d bar. Our null value is 0. If you have something and I take nothing away from you, you have whatever you started with. So our numerator is just d bar. So not only is it a special case of a one population mean problem, it is actually easier. And then our null standard error is the exact same as the standard error we used in our confidence interval. Once you have your test statistic, because this is essentially a one population mean problem, we use our degrees of freedom, we go to our table, just like we did back in chapter 3, and then our conclusion is always the same. If the p-value is less than 0.05, we reject the null and accept the alternative. If the p-value is greater than or equal to 0.05, we fail to reject the null and fail to accept the alternative. Always, always, always. So we will perform a hypothesis test to determine if the amount of computer use is different than the amount of television use for all students. Step 1, are all the conditions met? Yes. Does not matter if the data is normal. We have a sample size of at least 30. There's nothing inherently biased about taking a liberal arts course in statistical literacy. We'll assume that it's random enough. We have a quantitative variable, and we have paired data, so we are good to go. Our null hypothesis, mu sub d equals 0. There's no difference between computer use and TV use among all college students. Our alternative hypothesis, mu sub d is not equal to 0, or there is a difference between computer use and television use among all college students. Our test statistic is d bar divided by our null standard error, but we've already calculated that, so I did not recalculate it here. 15.24 divided by the square root of 35. What we use for our standard error up in our confidence interval, it's the same thing here. So our test statistic is 1.304. We go to our table, we use 34 degrees of freedom, and we find a p-value of 0.202, which is greater than 0.05. So we fail to reject the null. We fail to accept the alternative. There is not enough evidence to prove that mu sub d equals 0. Lab 8 will go over this information as well.